Hi everyone. So today I'll be talking about our Tokai paper, creating and augmenting keyboards for extended reality with the Keyboard Augmentation Toolkit, or CAT. My name is Mark McGill. I work at the University of Glasgow, and this was a result of a collaboration between the University of Glasgow and Logitech Design Lab in Ireland. So extended reality headsets are increasingly being used to drive productivity-oriented experiences for apps such as Big Screen, pictured here in VR, to Meta's Infinite Office functionality in Quest headsets built around progressive web apps and Android apps. Crucial to the use of such workspaces is text entry, and this predominantly requires a high bandwidth input modality, namely the physical keyboard. Logitech and Meta have worked on keyboards whose position and orientation can be tracked by XR headsets, enabling full seated desk-based productivity in VR, and this functionality can be used to render an interactive digital twin of the physical keyboard in VR, or can be used to selectively show areas of the pass-through feed pertaining to the keyboard, either way enabling direct use of this high bandwidth input peripheral in a VR or XR headset. But one advantage that has been somewhat overlooked is the capacity for these devices not just to present virtual displays or 3D content to the user, but also to augment or alter the peripherals and surfaces that they're interacting with. For example, if we know where the keys are, we can visually augment the keyboard in any way that we see fit. For example, rendering active shortcuts or visualizing different overlays or mappings. And if we have hand tracking, our capacity to interact with the keyboard also greatly increases, able to support interactions, for example, on or around the keys of the keyboard. Touch display keyboards was perhaps one of the earliest examples of augmented keyboards. This was enabled using projection on a physical keyboard, and the project supported a plethora of interactions, including multi-key buttons and temporary keyboard-based menus, all visualized directly on the physical keyboard itself. For interactions on and around the keyboard, projects such as Gestakey, Finger Arc, and Finger Chord have all exploited some capacity to track finger movements or receive additional input that can enhance our capacity for expression based on an interaction with a single key on the keyboard, going beyond binary key presses alone. However, the majority of the previously mentioned projects shared common drawbacks, particularly around the hardware needed to enable these interactions. So, capacitive sensing and per-keycap displays are common themes here, but integrating such technologies into keyboards is expensive, difficult, and not particularly sustainable, given we all have perfectly good keyboards right now. XR headsets, however, offer us the possibility of driving such activities without the need for additional hardware, beyond the physical keyboard itself. So Reconfiguration here demonstrated this when they rendered different character sets and different UIs on a tracked physical keyboard in VR. And building on this, the Keyboard Augmentation Toolkit is our first attempt to support the creation and exploration of XR-driven keyboard interactions, where the very form and function of the keyboard can be altered. So our aim was to have an open source toolkit that would enable practitioners to build novel augmented keyboard interactions and replicate and transpose previous research where applicable, taking advantage of the combination of the tracked keyboard and XR-enabled sensing such as hand tracking. Our toolkit works with the Unity gaming engine and supports the ability to define augmented keyboard interactions through creating new keyboard mappings. So keyboard mapping effectively describes what each key should look like and what it should do. And this can be as simple as having a mapping to show a different character set versus more complex multi-level hierarchies of key functions. For example, a Photoshop mapping might visualize its keyboard shortcuts by default, but overload keys with additional functionality when the color picker is open. And each of these mappings is made up of one or more key elements, where a key element denotes the set of interactions to be bound to a set of one or more keys. For hierarchical mappings, here we can see that the keyboard mapping is presenting emoji input, where the keys along the top of the keyboard all activate child keyboard mappings for different subsets of emojis. This gives us the flexibility not just to define new interactions, but also have those interactions coexist with others non-destructively. Key elements can display content in 2D or 3D across one or more keys, and can receive and react to an extensible variety of interaction event triggers, from simple binary key presses to hovering above the key, or gesture key style swiping or taps of the surface of the key, and so on, all without needing integrated capacitive or pressure sensing in the physical keyboard. So this is all driven by the hand tracking in relation to the tracking of the keyboard. These key elements can span multiple keys, creating interactive regions that support both discrete and continuous inputs on and around the keyboard, again driven by XR-enabled hand tracking. So here you can see a user interacting with each multi-key region with a Medeiros keyboard. And these keyboard mappings can be applied to any keyboard layout, be it a real physical keyboard that's being tracked by an XR headset, or a Medeiros virtual only keyboard. And our toolkit provides assistance in defining and generating these keyboard layouts, for example based on an existing digital twin 3D model. Now, I'm not going to go into great detail about CAT here, except to say that this is an open source extensible toolkit that provides a strong foundation for creating a wide variety of augmented keyboard interactions. To give an example, this is a screenshot of the new SIGCHI keyboard layout that was imported into CAT and visualized on an existing physical keyboard, a version of the Logitech Mixed Reality keyboard for Windows Mixed Reality. And it becomes straightforward to import, visualize, and switch between different keyboard configurations on the fly here, meaning the physical keyboard can adapt to the needs of the user, with the interface even extending to the keyboard rather than simply receiving events from the keyboard. And here we can see the same new SIGCHI layout applied to two very different configurations of mixed reality keyboards based on prior research. On the left here, this was a paper looking at mid-air keyboard input in VR. On the right, this paper was looking at keyboard input where the virtual interface was aligned to the surface of a table. And we can see that the mapping is applied equally to both of these different layouts. CAT facilitates the creation and further exploration of augmented keyboard capabilities. Our hope is that this toolkit represents the first step towards having augmented peripherals supported at an operating system level on XR devices, such that we might appropriate and augment keyboards, mice, and touchpads as part of our daily productivity experience when using XR headsets. Our paper goes into far more detail about the toolkit and our initial explorations of this space, so please see the Tokai paper for more details. Thanks.